Good evening, class. This is class 3rd of assignment 3rd in class 4. Of electronic theory of solids. In this class, I will be covering majorly the part of the Hall effect, which is classical. Then a few problems from the quantum mechanics. And then I will end the class with Bloch theorem. Yeah. So having said that, I'll start the class right away, and just a minute. Yeah. So last time we had it till the Fermi energy and the Fermi temperature. All those things we covered up to the assignment 2. And now in this part, we'll be covering Hall effect, the quantum mechanics problems, maybe 1, 2 or 3. And then finally the Bloch theorem, that is the electron in a periodic lattice and how the wave function evolves in those cases. So having said that, let me start with the Hall effect. Hall effect is nothing but if you have, let's say, a semiconductor bar in which you apply a potential with the battery B, then, and this is your point A, this is your point B, and similarly you can have point C and D also. So when magnetic field, let's say a penetrating magnetic field B is there, which is perpendicular to this your bar. So in that case, for B equal to 0, VA will be equals to VD, right? If the bar is homogeneous, generally like homogeneous, then in that case potential at A will be potential at D, same. And similarly, VB is equals to VC, right? But when magnetic field is non-zero, what you get is VA is no longer equals to VD, and VB is also no longer equals to VC. And this is the clear signature that the whatever element which is carrying the current in the system is a charge particle, because when a charged particles, let's say an electron, moves in let's say the x direction, let me define, and this is Vx and this is y coordinate. Let's say it moves in the x direction with velocity v, then the force on it will be F equals to q, which is the charge, times E cross B, QV cross B, sorry, V cross B. Okay. So in this scenario, when your positive potential is applied here, negative here, so electron will move in this direction, right? From negative to positive. So your V is essentially minus Vx cap. Let's say your B is perpendicular Bz cap, and your charge is electronic charge minus E. Then the force will be minus E. V is minus V, and B and X cap cross Z cap. This is nothing but EVB, and X cap cross Z cap will be minus Y cap. So in that case, electrons will drift toward this end. If they accumulate on this edge, AB edge, then the potential on AB side will be different from the potential on the CD edge, and that's where the transverse voltage comes in. This is well discussed in the class already. And the important point to note is there that even if the charge particle charges change basically, let's say now if a hole is there instead of electron, a hole is there with charge plus E instead of minus E. Now the charge is plus E. Then your V will be actually Vx cap, because now they will move in the direction of the battery, right? The direction of the electric field, not opposite. So this is how they will move the whole carriers. So V will be Vx, B is Bz cap, and Q is E. Again, the force turns out to be EVB minus Y cap, saying that okay, irrespective of the charge, all the charges will move in one direction only, and that's a good thing, because if now the electron is there and on the bottom is B, the negative charge will accumulate, and if hole is there, the positive charge will accumulate, and by reading the voltage VTB, that is between difference between T and B, one can tell that whether, so VTB sign tells if carriers are electron or hole. And this is what's like very conventionally used in the semiconductor case to determine the different types of the carriers. Yeah. So this is about the basic introduction. Now moving on to the solving the problem. Okay. So now the question is, now if you are doing a whole experiment in a whole effect experiment, in a metal, a potential of, that is the battery micro, okay, this is the potential between A and B, the top and the bottom edge is developed. This is very small voltage. If you see, it's only microvolt, but that's enough to tell us what is the number of the carriers there in the system, what is their charge, all those things it can tell. Foil of thickness 0.02 mm. Now it says that when a current (1.5 ampere) is passed in direction perpendicular to the magnetic field, of 2 Tesla. 2 Tesla is a large magnetic field. So generally 2 Tesla of magnetic field is achieved using superconducting coil magnets, not the conventional, because it requires large like amount of the current, and that current generally warms up the wires and they get burnt. So generally to attain the magnetic field above 1 Tesla, people use superconducting magnets where the heat loss is not there. So the Hall coefficient for metal is, so this is what the question is. So you have you are doing a whole effect experiment, of course with a metal. You can do it with a semiconductor also, but not insulator. Now a potential of 4.5 microvolt is observed. So this is Vxy, right, transverse to the current direction, and the thickness of the foil is also given, current passing through the foil is also given, and magnetic field is also given. All we have to do is determine the Hall coefficient. Hall coefficient, if you follow the class notes, is RH, denoted by RH, and nothing but EY by JXB. EY is the electric field in the Y direction, Jx is the current density in the X direction, B is the magnetic field. So you're having a geometry like this. Yeah, I think this is the geometry in which this thickness, this they have given to be 0.02 mm, extremely thin. I mean, so 0.02 mm is roughly 20 micron, and width also is there. Let's say it's W, and the transverse voltage which has been developed between X Y is nothing but 4.5 microvolt. This is all what you have. Now, if I ask you, how do you write the EY? Because here we need EY, JX, and B. Okay, let me write EY. EY is the electric field in the transverse direction. Electric field in transverse direction. JX is current density. B is magnetic field. Current density in X direction. B is the perpendicular magnetic field. Yeah. So if I ask you how to write EY, you will say that okay, EY is nothing but VXY by whatever the width is there, right? And similarly, I can ask you Jx also, how do you write the current density? Current density you write total current divided by the area, right? So W, which is the width, and T is the thickness. That will give you the area, right? And B is the magnetic field. Now you substitute these values. This is equation 1. Both of these are equation 2. Substituting 2 in 1. So RH is nothing but EY is VXY by W times W times T by I is B. W goes away, but we are left with is RH is equals to VXY, that is the transverse voltage, microvolt, which whatever the value is given. T is the thickness,